guys, it's IDW back, and today we're going to be actually continuing on in terms of actually getting to making a device that can add, and not like just all this logic that we've been messing around with. We're actually going to start getting into something that's going to be the end product of this series. Anyway, so we're going to have to do a bit of a memory refresh as to what binary was again. Remember, it's the counting system that we have to use because our wires only have 2 states rather than 10. It would be awesome if wires could be like that. Actually, they can be in real life, but it's actually easier to do binary, astoundingly. I know that most beginners would start crying when they heard that, but literally, it's easier. Anyways, so we're not just going to jump into addition right away. What we're going to start out with is something called incrementation, which basically means the ability to add 1 to something. So if I was to increment the number 1, then I would get 2. If I was to increment 2, I would get 3, etc., etc., etc. So what we're going to start doing is we're going to, first of all, look at all the steps of an addition problem. And then, actually, I'll show you what a truth table is first. So what a truth table is it's, if you've taken geometry, then you'll know what a truth table is. But it's basically a list of all the possible inputs that you can get for a logic gate. Remember when we were talking about binary, I went over how whatever your inputs are, there's a certain number of outputs that you can get. For instance, if I was to add another bit onto this, and I was to do like this, actually, like this, and then I could just do that. So there's 4 different possibilities. And what a truth table is it's just going to show you what the results are for wrong command, each one of those situations. So for instance, if I was to do like the XOR gate that we have right there, it's still inverted, so it's technically an XNOR. I would have that and that, like that. So the only time that it's on is if one of the inputs is on, right? So if there's both on, no input, output, none on, no output. So this right here would be the truth table of an XOR gate. So now we're going to actually move on to actually adding. So I'm just going to, with binary, I'm going to actually do an addition problem, the same way that you would add 2 numbers in decimal. So if I was to add a 1 to this, then I would get a bit that I can't get. It would be like adding 5 plus 5. I would have to carry it over to this bit. So that's exactly what I'm going to do. So then I have to add this to this, of course. Oh yes, and I put a 0 here just because right here there's actually not going to be anything in this bit. Just like if I added 5 plus 5, I would get 1, 0, and not anything here. So yeah, that's why I'm not putting anything there. Anyways, so now we have a value right here that we're adding to this right here. So now we're just adding these 2 numbers together, and it's the same situation as we had before. So we have to carry it over to the next bit again. It would be like we added 45 to 5, and then this right here has 50, so it carries over to the next bit. So that means that we don't add anything to it here, though, so this does actually result in a 1, or in this case, a 100. So far, we've added 5 plus 45, basically. And then there's another bit right here, which is basically like a random 1000. So there isn't anything to add to that, so that just comes down here. Now, I haven't actually done anything on decoding binary, but it's just like in decimal. This is your 1's place. This is your 2's place, this is your 4's place, and this is your 8's place. just like in decimal, you'd have ones, tens, hundreds, thousands. Anyways, so what this means is that, sorry about that. What this means is that if I was to just try to represent 1,000, for instance, as a string of, just one number, then I would represent, then I would have 1,000 different, sorry, so let's say this was 1,100, right? If I was to have a whole bunch of individual wires, if each one was to represent one, then I would not just do 1,000, I would do 1,000 plus 100. So the way that you actually calculate what something is in decimal is you take the place value of that bit, and if there's a 1 in it, you add the place value to your initial number, and if there's a 0, then you don't add anything. So 0 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8. So that would result in 12. Oh, and I am going to have to pick up a phone really quickly. See you guys in a sec, sorry. Okay, I'm back. The phone call was no one. Anyways, so, back to this. So this is a binary 12. And if you look at the problem right here, we have 1 plus 1 plus 8. That's 3 plus 8 is 11. Plus 1, that's the actual addition sequence that we're doing, should equal 12. And this is 12 right here in binary, as I just showed. So yeah, everything works just fine. So now we're going to actually move back to the truth tables, because now we actually have, we know what's going to happen in every situation, basically. Well, now that I've shown you how it works, we can easily see what's going to happen in each situation. So if I was to have a truth table like this, we're going to be doing every single result that we would get if we were to do just a simple addition. Because the way that this is initially going to work, well, eventually going to work, is that we're going to add each one of them and add them at the same time, and then we're going to add in any carries that we get, that we result in. So yeah, that's basically what that is. So this is just going to be the thing that if we have two numbers that we want to add together, this is what it's going to give the result. Because that should be a basic logic gate. Because there's no special circumstances. So initially this is the first addition thing, not counting the carry. So if we were to add 0 plus 0, we would get a 0. If we were to add 0 plus 1, we would get a 1. And I gotta stop doing that. Anyways, 0 plus 1 again, we should get a 1. 1 plus 1, this is like 5 plus 5. We would get 10, which is 1, 0. So in this place, we should have a carryover, because this is the only case in which a carry can actually be created. Because in all the other circumstances, it's enough that it's going to be, if we were to add them together, it would be quote-unquote less than 10. So yeah, this is the truth table for the thing that's going to add our two numbers together. Now, we just built a truth table over here, and look at this one. Notice any similarities? Yes. Anyways, so that is why I actually wanted to build this thing, the XOR. Now, technically, there are a few ways that you can use 2 XNORs instead of 2 XORs. I actually use that in my, the adder that I showed off as my first video ever. So, yeah. But for the moment, we have just proven that the thing that we need to use in order to do this simple addition process is just an XOR gate. But I also explained that the only case that we're going to get anything that's going to be able to bring it over to the next bit is if we're adding this plus this. So in the next video, what we're going to be doing is we're going to be using this logic that we've created here to actually build something that's going to be able to add 1 to whatever we want it to be. So, see you guys next time.